Hello everyone. So today we are going to deal with a simple problem from beam analysis, and the problem is draw axial force diagram, shear force diagram and bending moment diagram for the given beam and show salient features if any. So here we are given a simple beam loaded with different kinds of loads as shown in the figure, and we are asked to perform complete analysis of the internal forces axial force, shear force and bending moment which are generated in the beam due to these loadings. So first let's take a look at the loadings. We have UDL, uniformly distributed load of 6 kilonewton per meter at portion AB of the beam, and a point load of intensity 10 kilonewton at point C of the beam. Also a point moment of 20 kilonewton meter at point C, and finally a point load of intensity 20 kilonewton at point E. Due to these loadings, internal forces like axial force, shear force and bending moments are developed along the span of the beam. Now, after we have studied the loads, we are going to take a look at the supports of the beam. Here we have two supports, one at point A and other at point D. The support at point A is a hinge support and that at point D is a roller support. So what do these supports do? A hinge support resists motion along horizontal and vertical direction but cannot resist a rotating motion. So reaction forces that are developed at hinge support are along horizontal and vertical direction. Let's say Rax be the reaction force along horizontal direction at point A and Ray be the reaction force along vertical direction at point A. And what does a roller support do? A roller support resists motion only along vertical direction and does not resist the horizontal motion and rotating motion. So only reaction developed at roller support is along vertical direction. Let's say Rdy be the vertical reaction force at point D. Now for the analysis of the internal forces on the beam, we need to find out the values of these reaction forces at first. How can we find the values of these reaction forces? Now we are going to use the equations of static equilibrium for the calculation of these reaction forces. We have the equation of static equilibrium are summation Fx is equal to 0, which means the summation of all the horizontal forces on the beam is equals to 0. Summation Fy equals to 0, which means summation of all the vertical forces acting on the beam is equals to 0, and summation m equals to 0 is the moment equation, which means summation of moment about any point of the beam is equals to 0. Let's proceed to the calculation of reaction forces. First, we are going to calculate the horizontal reaction Rax at point A. For the calculation of Rax, we are using the first equation of static equilibrium, which is summation of all horizontal forces in the beam equals to 0. But in the figure, we see that only horizontal force in the beam is Rax. So we obtain Rax equals to 0, which means there is no horizontal reaction at point A. Now we have other two reactions left are Ray and Rdy, both acting in vertical direction. So for the calculation of these reactions, we are going to use summation moment equals to 0 first, but not the summation of vertical forces equals to 0, because if we used summation of all the vertical forces equals to 0, we are going to obtain an equation containing both of these unknown reactions Ray and Rdy, and it would be tedious to calculate the value of these reactions. So first we are going to use the moment equation first. Here the moment equation is summation m moment about any point of the beam equals to 0. Let's take the moment summation of moment about point A equals to 0 and consider all the clockwise movements positive. So using this equation we obtain the equation. First I am going to explain this equation to you all. This is nothing but the summation of moments due to all the forces in the beam about point A. Simply, how do you calculate a moment? You multiply any force with its distance from a point about which moment is required. Here, the first term is 6 times 3 times 3 by 2, which is moment due to UDL at point A. Here, our UDL has intensity of 6 kN per meter and is distributed through the length of 3 meter. So total force due to this UDL is equals to 6 times 3, which tends to act through the center of the UDL, which is a distance of 3 by 2 meter from point A. So moment due to UDL about point A equals to 6 times 3 times 3 by 2, just the multiplication of force and distance. And in this equation, our second term is 10 times 4, which is moment due to point force of intensity 10 kN about point A. Since it is a distance of 4 meter from point A, we multiplied its intensity 10 kN with 4. And the fourth term in this equation is 20, which is the point moment at point C, which is of intensity of 20 kN meter, and it is acting in clockwise direction. Since we consider all the clockwise movement as positive, we just added to this equation, and the fourth term in this equation is RDY times 5. This is the movement due to this reaction force RDY about point A. Since point D is at 5 meter distance from point A, we multiplied this force RDY and distance 5 meter to obtain moment due to RDY. But you can see here we have taken this moment due to RDY as negative, because you can visualize here that it tends to rotate the beam in anti-clockwise direction, while all other forces and movements tend to rotate the beam in clockwise direction. So all other forces are giving clockwise movement about point A, but this reaction force RDY is giving anti-clockwise movement about point A, so it is taken as negative. And finally, we have the last term 20 times 7, which is just movement due to this point force 20 kN about point A. It is also taken as positive because it gives clockwise rotation, clockwise movement about point A. So on solving this equation, we obtain the value of RDY equals to 45.4 kilonewton, which acts in upward direction. Here we consider the original direction of RDY as upward, and we obtained the value, positive value of 45.4 kilonewton. So our original direction of RDY was correct, and it acts in upward direction. Now, after we have obtained the value of RDY, the only reaction left to calculate is RAY. So to calculate this equation, we are going to use the remaining equation of static equilibrium, summation Fy equals to 0, considering all upward forces as positive. Now, this equation is going to lead to the equation RAY minus 6 into 3 minus 10 plus RDY minus 20 equals to 0. Here, RAY is vertical force acting in upward direction. Since we considered upward direction force as positive, it is taken as positive, and 6 into 3 is force due to UDL and is acting in downward direction, so it's taken as negative. Also, our point force of 10 kilonewton is also acting downward, so it's taken negative. Now, RDY is the reaction force acting in upward direction, so it's taken positive. And finally, 20 kilonewton is point force acting in downward direction and is taken negative. And now, on substituting the value of RDY as 45.4, on solving this equation, we obtain RAY equals to 2.6 kilonewton in upward direction. Here also we obtained the value of RAY as positive 2.6 kilonewton, which means our assumed direction of RAY was correct, which is in upward direction. So in this way, we calculated the values of all the reaction forces in this beam. Here I have substituted these values in the figure you can see in place of RAY I have written 2.6, in place of RDY I have written 45.4, and in place of RAX I have written nothing because we obtained the value of RAX is 0. Now we are going to calculate axial force. First of all, what do we mean by axial force? Axial forces are those internal forces which act along the axial direction of the beam, which may be tensile or compressive. Tensile axial forces are those which tends to act away from the supports, and compressive are those which tends to act towards the support in axial direction. So now in the figure we can see there are no any forces acting in axial direction. So axial forces in any portion of the beam is equals to 0. That is, axial force at portion AD is equals to 0, and axial force at portion DE is also equals to 0. So now after finding the axial forces at various points, we are going to plot axial force diagram. To plot the force diagram, just simply draw a dotted line through different points of the beam as shown in the figure, and since axial force at any point of the beam is equals to 0, there is nothing to plot, so it is simply a straight line, no force at any point. Now after axial force we are going to move to shear force. First, what do we mean by shear force? Shear force is another internal force which takes account of all the transverse forces, or the forces that are acting in transverse direction with respect to the axis of the beam. If you need to plot the shear force diagram of the beam, we need to calculate shear force at each and every point of the beam. So how do you calculate a shear force? If you are willing to calculate shear force at any point, we need to do the summation of all the vertical forces on either left or right of that point. So for that, sign convention is, if you are calculating shear force from left side of the point, we take all the upward forces as positive, and if you are willing to calculate shear force considering forces at right side of the point, we consider all the downward forces as positive. So this is the sign convention for the calculation of shear force. So let's get started. One more thing, if you are calculating shear force at point where point force is present, then we need to calculate shear force at just left of that point and just right of that point also, because at just left and just right of that point shear force varies. So let's begin with point A. Here a point force of 2.6 kilonewton is present at point A. So first we need to calculate shear force at left of A. So to calculate shear force at just left of A, we do the summation of all the forces on left of that point, but there are no forces on the left of that point, so shear force at just left of A is equals to 0. Then we need to move to the second point, which is shear force at just right of A. So now we imagine ourselves at just right of A, and do summation of all the forces, all the vertical forces on left of that point. On left of just right point of A, there is only one vertical force, which is 2.6 kilonewton and acting in upward direction. So shear force at just right of A would be 2.6 kilonewton. Now we will move to our next point, which is point B. To calculate shear force at point B, we do summation of all the vertical forces on the left of that point. So on the left of B, we have a upward point force of 2.6 kilonewton and downward UDL of 6 kilonewton per meter, which is distributed through length of 3 meter. So on doing summation of these forces, we obtain shear force at B to be minus 15.4 kilonewton. Here we obtained the value of shear force at point B. But what about portion AB? Here we see that shear force at just right of A is equals to 2.6 and shear force at point B equals to minus 15.4. So shear force changes its sign somewhere between point A and B. So we need to find the point where shear force changes its sign from positive to negative. For that we consider a point at distance x from point A and assume that value of shear force at that point is equals to 0, so that shear force changes its sign at that point. So to calculate the value of x, we need to uh, equate the value of shear force at that point with 0. So equating value of shear force at that point equals to 0, we get 2.6 minus 6 times x equals to 0. This is the value of shear force at distance x from point A. Here we have done the summation of all the vertical force on left of that point. On left of that point we have one vertical force is point force acting in upward direction, which is of intensity 2.6, and other vertical force is UDL, which is acting downward and having intensity of 6 kN per meter. And since we are considering forces on left portion of that point, we are going to multiply with 6 with x, because we are only considering forces on left of that point. So on solving this equation we get x equals to 0.433 meter point A. So shear force changes its sign at 0.433 meter from point A. Now let's move to our next point. Our next point is point C, but due to the presence of point force of 10 kN intensity at point C, we need to calculate shear force at just left and just right of point C. At just left of C, we have the forces shear force equals to 2.6 minus 6 into 3. Here we have done the summation of all the vertical forces on left of C. We see that on the left of C, one vertical force is 2.6 and other vertical force is UDL of 6 kilonewton per meter, which is distributed through the length of 3 meter and is acting downward, so it is taken as negative. So shear force at just left of C equals to 2.6 minus 6 into 3 equals to minus 15.4. Here shear force at point B and just left of C are equal. Now shear force at just right of C equals to 2.6 minus 6 into 3 minus 10. Here we considered all the vertical forces on left of this point just right of C. So the value is 2.6 minus downward UDL force 6 into 3 minus downward point force 10 kN, which gives the value minus 25.4. Now next point is shear force at just left of D. At just left of D, we have again considered all the forces on left of that point. On left of that point, we have got vertical forces 2.6 upward and UDL force of 6 into 3 downward and point force of 10 kN downward. So it is equals to minus 25.4. And on just right of T, again considering all the vertical forces on the left, we have 2.6 upward, 6 into 3 UDL force downward and 10 kilonewton force downward and a point force which is on point D of 45.4 kilonewton which is acting upward, so it is taken positive. So we obtain shear force at just right of D equals to 20, and at just left of E, again considering forces on left side of that point, we obtain shear force at just left of E equals to 20, just as above. And at last shear force at just right of E equals to performing calculation just as above, we obtain at just right of E shear force equals to 0. So we obtain shear force at each and every point of the beam. Now for plotting these values in shear force diagram, we are back in our plotting page. So we draw a straight line first and we obtain these values just now by calculation. So we are going to start plotting. Here shear force at just left of A equals to 0 and shear force is just right of A equals to 2.6 positive. So here is 2.6 at just right of A. Left was 0 and at just right it was 2.6. So we move 2.6 meter upward. And at point B we had minus 15.4. So we came minus 15.4 from point B downward and joined it with our previous point from point A. This is minus 15.4. Again at point C we have minus 15.4. So we again joined this point with our previous point, and at point just right of C we have minus 25.4. So it goes further down to minus 25.4. Now at point just left of D it is again minus 25.4. So we are going to plot right just as before. So it is also minus 25.4. We are just joining those lines and points, and at just right of D we have positive 20. So it goes upward and upward to the distance of 20 meter from the axis or neutral 0 axis. It is 20 upward, and at just left of E it is again 20 and it goes right just as before to 20, and at last at right of E it is equals to 0. And Vx shear force equals to 0 at x equals to 0.433 meter point A. Here shear force changes its sign at 0.433 meter point A. You can see between portion AB, at portion AB between point A and B, shear force changes its sign at distance 0.433 meter from point A. Here this portion is positive, this is negative, and this is again positive shear force. So this is our shear force diagram. Now we are going to calculate bending moment to draw the bending moment diagram. Now what do you mean by bending moment? Bending moment is another internal force that takes on account of bending effect due to all the forces in the beam. How do you calculate a bending moment? Calculation of bending moment is just like calculation of shear force. Only difference between them is that in case of shear force we calculated force at all those points, and in case of bending moment we need to calculate moment at all those points, and calculation is same as shear force. And let's talk about sign convention. For calculation of bending moment, sign convention is that if you are taking account of all the forces on left of the desired point, we take all the clockwise movements as positive, and if you are taking account of all the point on the right side of the desired point, we take all the anti-clockwise movements as positive. So this is it. So let's begin. And one more thing, in case of shear force, we calculated shear force at just left of the point and just right of the point in case there is presence of point force, and in case of bending moment we need to calculate bending moment at just left of the point and just right of the point if there is presence of point moment at that point. Here in case of our beam there is presence of point moment at point C only, so we need to calculate bending moment at just left of C and just right of C, and at all other points we don't need to calculate bending moment at just left and right. So let's begin. First of all, movement at point A. Now to calculate bending moment at point A, consider force on left of A. Since there are no force on left of A, bending moment at point A is equals to 0. Now let's move to our next point, which is point B. Now just like in case of shear force, considering forces on left of B, we have 2.6 kN force and UDL force of intensity 6 kN per meter. Since our sign convention is that forces which cause clockwise movement are taken as positive and those which cause anti-clockwise movement are taken as negative. So we are finding bending moment about point B. You need to visualize it that if you are calculating movement from point B, you see that 2.6 kN force causes a clockwise movement. So movement due to 2.6 kN force about point B equals to 2.6 into 3, because distance of 2.6 kN force and point B is 3 meter. And also movement due to UDL force is anti-clockwise direction. It gives negative movement. As you can visualize, if you are calculating movement about point B, it gives negative movement, and whose value will be equal to 6 times 3 times 3 by 2. It is just as our previous case, calculating movement about point B. Here total force due to our UDL is equals to 6 into 3, which tends to act about the center point, which is at distance 3 by 2 from point B. So movement due to UDL force equals to 6 times 3 times 3 by 2, which is negative because it is acting in anti-clockwise direction. So bending moment at point B would be minus 19.2. Now we are going to move to our next point, which is moment at point C, at just left of C, because there is presence of a point moment at point C. So just as previous case, considering all the forces on left of point C, we have bending moment at point C equals to 2.6 times 4 positive, which is clockwise direction, and bending moment due to UDL force equals to total force into distance. Total force is equal to 6 times 3, and distance of that force from point C is equals to 1 plus distance from center of UDL to point B. Here 3 by 2 is distance of center of UDL to point B, and 1 is the distance from point B to C. So simply add those distances to get distance from UDL to point C. So it gives the moment equals to minus 34.6, which is the bending moment at just left of C. And at just right of C, here we have taken account of forces on right side of that point. So just as I said before, if we consider forces on right side, our sign convention is anti-clockwise movement is positive if we are considering forces on right side. But you can see 20 kN force at point E gives clockwise movement about point C, so it is taken as negative, and another point force 45.4 kN at point D gives anti-clockwise movement about point C, so it is taken as positive. So on calculation, we obtain value minus 14.C. Here we have done this calculation by different process than before. In all previous cases, we consider forces on left of that point, but in this case we have considered forces on right of that point. Please be careful using the sign convention. So now we can move to our next point, which is point D. Moment about D equals to minus 20 into 2. Again we have considered forces on right of that point. So moment due to 20 kilonewton force at E would be minus 20 times 2. Just force into distance is equals to minus 40. And at point E it is equal to 0. We can see no forces on just right of E. So there is no bending moment at just right of E. Now we calculated bending moment at all those points, but what about portion AB? What about all those points between point A and B? We need to calculate bending moment at those points, but it is impossible to calculate bending moment at all those points. So we are going to find the nature of bending moment at that portion under the UDL. So consider any point at distance x from point A between portion A and B. Now we need to find the value of bending moment at that point so that we can identify the nature of bending moment between point A and B under the UDL. So how do you calculate bending moment at that point? Simply we calculate bending moment at that point just as before. Considering all the forces on left of that point, we have the forces on left of that point are 2.6 kilonewton point force acting upward and 6 kilonewton per meter UDL acting downward. So we just do the summation of moments due to those forces. So here point force of 2.6 kilonewton creates a clockwise movement of 2.6 times x at that point. Just the multiplication of force and distance. Force is 2.6 and distance is x. And UDL creates anti-clockwise movement, so it is taken as negative. And how is it calculated? Here you can see 6 into x is the total force created by UDL, because we are only considering the portion of UDL on left of that point. So on left of that point its span length is x, so total force due to UDL is equals to 6 times x, and this force tends to act from the center of that span of UDL. So we see that distance x by 2 from our desired point. So distance is equals to x by 2 and total force due to UDL is equals to 6 times x. So moment due to UDL would be 6 times x by 2. So from this we would obtain moment at that point equals to 2.6x minus 3x square. So this value is not linear. We see that this is this is not a linear equation. This equation leads to the formation of parabolic line. So we identified that the nature of bending moment between point A and B is parabolic. So now we can use this equation to find the value of bending moment at any point between point A and B. For example, if we need to find the value of bending moment at point F, which is midpoint of AB, we can just substitute x is equal to 1.5, because 1.5 is just center point, which is middle point of 3 meter span, which is half of 3 meter, 1.5. So substituting x is equal to 1.5 in this equation, we get bending moment at point F equals to 2.6 times 1.5 minus 3 into 1.5 square equals to minus 2.85, which is the value of bending moment at point F at the center of the UDL. So we have obtained the value of bending moment at various points of the beam. So we are going to plot those values in the bending moment diagram. Let's see. First we are going to draw the straight line, and we obtain these values here. So now how are we going to plot these values in bending moment diagram? Simply, just as in case of shear force diagram, we are going to locate these points and join these values of bending moment at different points just as in case of shear force diagram. But between point A and B, can we join these values with a straight line? No, because we just obtained that we just identified the nature of bending moment between point A and B is parabolic. Under the UDL, the bending moment diagram would be parabolic. So we can join the values of bending moment at point B, A and B with a parabolic line, but not with a straight line. But how do we find out that the parabola would be concave upward or concave downward? So for that, here is the technique. If we were allowed to join point A and B with a straight line, what would be the value of bending moment at point F? What would be the value of ordinate at point F? It would be half of bending moment at point B, which is minus 19.2 divided by 2 equals to minus 9.6. But our actual value of bending moment at point F is minus 2.85, which is numerically less than 9.6. So our plotting point at point F is lower than if we were allowed to plot join the lines with straight line. So our parabola would be like this. So we see that our parabola would be concave upward if we plotted MF equals to minus 2.85 and MB equals to minus 19.2. So under the UDL, the nature of bending moment is parabolic. So now the UDL portion is over, so we can continue just as in case of SFD. So what is the value of bending moment at just left of C? It is minus 34.6. So we locate minus 34.6 and join it with the value of BMD at point B. Join it with previous line. So it would be like this. It is minus 19.2 here, and at just left of C it is minus 34.6. Now at just right of C it is minus 14.6. So we look at minus 14.6 at point C and join it with our previous line. It would be like this. So it is minus 14.6, and again at point D it is minus 40. So we are going to look at 40 first at point D, just above point D. We are going to go 40 upward from point D and join it with previous line. So it is minus 40, and at point E it is again 0. So we are going to join it with point E. We are not going to go either upward or downward from point E because it is 0. So it is all negative. Bending moment we obtain all negative. So it is negative and it is negative. So this is our bending moment diagram. So now we plotted axial force diagram, shear force diagram and bending moment diagram for the beam, for given beam. So we are going to go for salient features. What were the specific unique features of the loadings in the given beam? It was that shear force equals to 0 at x is equal to 0.433 meter from point A. Our shear force diagram change its sign from positive to negative at 0.433 meter from point A, as you remember. So it is our one unique salient feature, and another unique feature is that bending moment is maximum, which is 40, which is numerically highest value, as you remember, as you just plotted the bending moment diagram. At point D it was maximum. So this is our salient features. So this is it. We have finally completed plotting the axial force diagram, shear force diagram and bending moment diagram for given beam. This is complete analysis of internal forces due to given loadings. So thank you very much, guys.